and set the stage for today. So in our last session, we actually talked about probabilistic perception. We introduced Bayesian network, and we discussed about Gaussian likelihood prior, and how we can actually make life easier using actually Gaussian distribution. But today, we're going to continue that because we need to finish it. That's a very important topic in robotic perception. But before we dive further into graphical models and talk more advanced topics about that, we need to step back a little bit and review LiDAR camera fusion because you need it for your last project. We talk about actually transferring between camera space and 3D space a lot, but we didn't talk specifically about LiDAR, but it's very similar. So we're going to talk about that, and then we move to, again, graphical probabilistic perception. So let's get started. First, we need to see what is the pipeline for LiDAR camera fusion. So you have some data that come from LiDAR and some cameras, some videos from camera. Most of the time, the system that you are using is kind of attach these two sensors together, but if not, still the process is same. And the first step is time synchronization. We need to synchronize the time. We need to synchronize time between LiDAR and camera. That's important, like when I'm talking about camera, that frame of camera and that frames of LiDAR. So since LiDAR and camera normally run in different frame rates, so we always need to synchronize them. Most of the time LiDAR is like 10 hertz, like 10 frames per second, and cameras is much faster, mostly 30 or 60 hertz. So we need to find what is the best match in this too, because we need to match them if you want to fuse them, if you want to like transfer some pixels from LiDAR to camera or camera to LiDAR, you need to do this attachment. Other than that, especially if the targets are moving, it's gonna be so messy. If it's a little later, you can do that nicely. We can see that in real situation. So that's the important part. Another thing that is very important, especially when you are dealing with actually, if you don't have information about the position of the camera or those kind of information that consider extrinsic information. So calibration in terms of extrinsic is another step. That is one of the most important part actually. Extrinsic calibration, this gives us the information about the rotation matrix and also translation vector. The translation is a vector that actually helps to can transform points from LiDAR coordinates to actually frame coordinates. So we have two coordinates, frame coordinates or image coordinates and LiDAR coordinates, and they are different. and we need to transfer from these two. And how we can do that? Using extrinsic information. Extrinsic information consider rotation matrix and transformation vector. These two, we need to compute that. How we compute that, we will talk about it. After that, we need still, even though we have 3D point in camera space, it still is 3D. So we need to, if you want to show it in 2D image space, we need more information, and that's information coming from camera information. Camera information like principal point, focal length, coming from camera. Intrinsic information most of the time is available in camera information, and if it's not, it's still the same way. You need to calibrate your camera to find those as well. We had some experience regarding that in previous assignments, if you remember, so you know how to do that. And then after that, since the LiDAR points are a cloud of information, lots of information, sometimes we need to filter them out. Not all LiDAR points are useful, okay? So we typically need to remove some points, and the points that are too far or too low, for example, or outside of fields of view, we can remove them. And this is actually is important. And at the end, we need to do projection. So projection means finally find, when we have transformation, we can see any points in LiDAR, like a point cloud can move to the image, or vice versa. So using this information, like intrinsic information and extrinsic information, let you to do this transformation, this projection nicely. And we can use coloring, like for example, based off the height of that, do coloring, or maybe we take colors from image and show it in 3D space of LiDAR space. We can do all of these tricks, or we can do triangulation to make triangles a space, you know, and do lots of amazing things with this information that we have. So that was the general view of all the steps. So let's go one by one with more details. So time synchronization is, we already talked, they are so LiDAR and camera are not in the same time. The rate are different, the timing sometimes different. We need to arrange this timing, we need to synchronize that nicely. And how we do that, I have a code written, and is in your actually lecture notes. If you look at lecture notes, I put all the code. If you want to use it for your project, you can do that as well. In my in that I used, actually I find LiDAR times and camera times and found the mean. We found the difference between it and found which one is the mean, and that time considered as an index time, and the frame and LiDAR in that index are most closed frames that together. So this is how I used, but still need some arrangement. After even choosing that, you need to do some try and error and see if they are matched very nicely. So this is the first step that you can do. The second step for spatial calibration or finding extrinsic matrix, there is some methods that you can use. As I mentioned, this extrinsic information are two parts: rotation matrix and translation vector. And these extrinsics actually help to move from LiDAR frame space to camera frame space. How? Using that. Positions, again, we are in 3D. 3D points in camera are 3D points in LiDAR multiplied by rotation plus T. So this is how we are transferring between camera and LiDAR. And how find R and T? R and T are not always available. Sometimes available, sometimes when you have, for example, a device that is already assembled together, like they have proper position for LiDAR, proper position for camera. So the factory is always, the factory that assembled these parts, they give you information like factory calibration. That's the best things that you can have in the simplest way. But it's not always available. It's not always the factory available. Sometimes you are doing by yourself. You are designing the hardware and you want to actually find this calibration. We call them a spatial calibration because it's depend on the space. So this rotation and transportation vector are important. So this is factory calibration. The second way to find that is to estimate that. We can estimate that manually by selecting some corresponding points in both of LiDAR space and camera space, and then find, based off the number of points that we selected, we can make some equations and mathematically solve it to find R and T. This is another way. So another method that is we use in this code that I'm going to show you in the next slide, we use OpenCV library or function called solve PNP. Solve PNP is doing all math by itself. You just give lots of points, at least 6 points in LiDAR space, and 6 points or more in actually image space, match them together and give them to solve PNP, and solve PNP gonna solve by itself and give you rotation matrix and transfer T actually translation vector. So this is what we use, and it's actually more popular method that we are using. If you have more matching points, it should be more precise, especially if you choose different depth for camera, for LiDAR and camera, and that's going to be so helpful. There is also other methods that can be used, like some calibration tools that we can use, like AutoWare or Calib are also other methods that we can use. They are very advanced. But most of the time, this solve PNP is easier to implement and is in hand and is free and you can use it. So let's use this solve PNP and see how that works. So I use that in actually data set that I share with you guys, and I just choose one frame. Just in one frame, I synchronize the time first between LiDAR and camera, and manually select multiple points. Here is 8 points, but you can see here just 7 points of that. And as you can see in 3D space, also you can see this corresponding to each of these points. I choose them. And when I select them, the rest is all actually make them as a vector or matrix and give it to OpenCV CV2 solve PNP function. As you can see here, we get these two and some parameters. And the result, as you can see, is R and T. And this R and T can be used for actually projection. So, but for projection, we also need camera intrinsic. So the camera intrinsic also needed to move to 2D space, U and V. If you remember when we talk about the image processing and transferring from real space to the image space, we talk about that. These two formula coming from that. If you want to actually transfer from 3D camera space to 2D image plane, you need a focal length and also principal point of camera, C x and C y, and f of x and f of y. So how we can find them? This information most of the time are available. If not, we can do the same method for calibration. We did that before. But here we had that. They were available. So we use them so we can use U and K and then corresponding points. When I transfer that, this picture is not actually very precise, but still is not bad. However, the LiDAR information probably overlapping kind of. I don't know how. For your project, you can use this information or not. You can choose any open source data set available. There's lots of them available. I just looked last week and I found so much. I can share with you too if you want to use them. And those data set also extrinsic information are available, so it's easier to work. I can share with you maybe today one of those if you want to work your project based off those, not this. But if you work with this, you're gonna have practice of this find this extrinsic and intrinsic and transformation and projection. That is not fun, but still is good to know. Kind of in terms of learning is important. Okay, so that was some information about your final project. I hope you learned something. It can help you. But if you have any questions, let me know. Other than that, we can move on to another topic. Any questions? Any concern? Let's see here in the chat. Okay, nothing here. Okay, don't see anything. Okay, good. Okay, no, nothing. Okay, let's go back to next part. But let's talk about probabilistic perception. So this topic that I'm talking about, probabilistic perception, I can say that one of the important things that most is very advanced method of perception, very realistic, and you can see how we can use that practically in so many applications, not just robotics, so many other applications. Anything probabilistic can be modeled using simplified using factor graph and use factor graph for optimization. So we're going to talk about that today. But what is factor graph? Last class we talked about probabilistic perception and graphical model to show that. We said, okay, all the story coming from joint probability. Joint probability of multiple random variable can be summarized or can be factored using product of some conditional probability. And that's coming from actually Bayes rule. And with Bayes rule, you can find relationship between this conditional probability and prior information or measurements likelihood. We talked about that before. We also talk about how Gaussian distribution can help. And most of phenomena in real world are Gaussian. So that's amazing. Gaussians are very useful because it gives you very the outputs are very precise and very nice. As far as they are following this Gaussian assumption, you can simplify your math and make them very good prediction, very similar, like a precise. It even doesn't need estimation. It even doesn't need approximation. It's just get closed form solution. But today we want to talk about another graphical model. So, and we want to see why this graphical model that called factor graph is better in terms of our application, that is robot perception, and sensor fusion. So we're going to talk about factor graph today and the rest of the classes that we have. We're going to see how we can model multiple sensors using factor graph and why factor graph is actually a kind of evolutionary method that can solve most of problem that we have in robotics and perception. And we're going to see why. And I really think that factor graph is the future of perception in robotics. So it's better to know that very precisely and use it in a real application. But what is factor graph? Factor graph is just the graph, is a graphical method to represent a function and breaking down a function to simpler functions that we call them factors. So first introduced by Xingshang and actually his colleagues back in 2001. The cool thing about factor graph is that it is a bipartite graph. What bipartite means the nodes are not all the same. We have different type of nodes. Some nodes are actually states, the one that we want to estimate, and some actually nodes are actually factors. So we have factors as a node and states as a nodes and relationship between these nodes. And factor graph is not directed graph. And also we can have loop. So this loop gonna give you lots of advantage. We're gonna see that soon. So that's the structure of factor graph. So factor graph is a bipartite graph, and it represents how a function, specifically a probabilistic function, can break down to smaller functions that we call them factors. So generally, if mathematically we want to explain factor graph, we can say, okay, a function like g of x, here is a posterior function. When I'm talking about posterior function, means probability of some unknown x given some noun z. X is unknown, we call them a state, and z is noun and measurements. And this g can be p, can be probability, but factor graph is not just for probability, it's for all functions can be implemented with multiplication of these factors. And this mathematical representation can be go to a graph. You can show that with the graph. In this graph, as you can see, some nodes are empty circles. Those empty circles are, we call them a state. A state normally showing the minimum numbers that you can represent a system. Like here, for example, is a position of the robot that moving in a different time. x0, x1, x2, x3 are, for example, can be position, x0, y0, x dot 0, and y dot 0. Okay, if it's constant velocity model, if they are moving in a constant velocity model. Yeah, so x0, x1, x2, and x3 are vector by itself. So let I clean this. I don't want to make it more complex. So this is the factor graph. So we have some nodes. Those empty circuits are states. And some field actually shapes like circles, diamonds, rectangle, triangle, whatever. Those are factors. So what is these factors? These factors are little information about that random variable. So these x1, x2, x3 are random variables, are states, but also random variables. But factors are not random variables. Factors are just a function, give you some information about that state. Like for example, if these states x0, x1, x2 are the position of the robot, this diamond factor showing the prior information about this. For example, a start point. The circle one is showing obstacle avoidance, for example. Obstacle avoidance factors, showing the closest obstacle to that. This rectangle one, or a square one, this square one between x1 and x2, showing the dynamic transition between x1 and x2. Like how we are moving from x1 and x2. Like coming from velocity and acceleration and those things. And so forth. As you can see, these factors, like for example, these three related to x1, x0, and these three are related to x1, and so forth. So as you can see, just limited number of factors are related to each state. So this is very important in robotics. This is showing that this is sparse. When I'm talking about sparsity, means each state just related to very limited number of factors. Because I said factors are some little information about states. So little information about the state. Like for example, information about the closest obstacle to that state, or for example, I don't know if it's a boat, for example, the position of the boat. One of the factors can show, for example, the wind in that position, or the current of the river or lake or ocean, whatever, and or other stuff, whatever happening in. That's why we call them factors, because they are affecting the sense, affecting the state, but not all the states. That little state, that one of the states, but they are all together make an optimization problem that very nicely. I think last class I talked about MAP problem, maximum a posterior problem, and MAP, and I think we talked about that, but if not, is okay. We're going to talk about that again. So I'm going to say factor graph at the end gonna change to a MAP problem, maximum a posterior problem. So and solve very efficiently. So because in maximum a posterior we are actually maximizing, actually argmax, posterior density P of x given z. We are maximizing this to find x, and this x is optimal x. However, it's not really optimal, it's approximately optimal. Why approximately? Because most of the time we are considering Gaussian assumptions. So, and this can break down to argmax. If you use Bayes formula, this is going to break down to P of z given x multiply P of x, and this P of z given x is a likelihood of measurements, and P of x is prior information about x. So prior about x and likelihood of measurements based off Bayes formula, this is actually consider, this is x. This is called maximum a posterior estimation, MAP. Maximum a posteriori estimation. Maximum a posteriori estimation is this one. It's very simple and at the same time very powerful method to actually estimate. Actually, you know what is doing? MAP changing probability to optimization, kind of changing probability to optimization, and that's amazing things. And factor graph is very aligned with this this MAP formulation. Why? Because this likelihood as priors, they are all considered factors. But we don't have just two, we have a lots of them. Doesn't matter, because P of z given x, that is likelihood. If we have lots of z's that are independent, they easily can break down to product of multiple factors, and they are all factors. For prior, the same too. If you have many priors, we just need to multiply them together. That's probability. When two things are independent, the probability of join is product of those. That's coming from probability rules. Okay, so that's why the factor graph becomes so useful in robotics, because in robotics, if you are dealing with uncertainty, most of the time the problem is going to break down to maximum posterior, and maximum posterior can be implemented by factor graph, and in factor graph you can solve this problem very easily. Not very easily, but easily. So let's see how. Also, last class, let I finish this and then go to the next. Last class also we talked about how we can solve that. We said, okay, if we consider Gaussian is the main point. Gaussian assumption gonna help us. If P of Z is Gaussian and P of X is Gaussian, we can write X star is equal to actually argmin. We change it to minimization and get minus log, minus L of n, or log, minus log of all of this. And minus log, if they are Gaussian, because Gaussian is exponential, log of exponential gonna get exponential, cancel out exponential, just exponent gonna stay. And this gonna summarize to argmin x sum square square values. Those squares are Mahal distance, if you remember last class, like sigma 1, sigma 2, and so forth. And problem gonna break down to minimization of sum of a square. Instead of nonlinear exponential family, we change it to the sum of a square. And sum of a square problem, minimization of sum of a square problem, is a very well-known problem that easily can be solved with so many methods, like including Gaussian Newton method is one of the methods to solve that. And when you solve that, you can find it. We're going to talk about that more in practical way. I just wanted to mention that to see how factor graph is aligned with this method, this maximum a posterior. Okay, so let's clean this up. And yes, so this factor graph contains variable nodes, factor nodes, and edge. Variable nodes are empty circles. Factors are squared or circles or other shapes, but filled. And edges are connection between factors and states. Two states are not directly connected together. That's important. Like x1 and x2, we don't have this. We always have a factor between, like x0 and x2, x1 are connected within a factor. Factor is connected to states, but not to states together directly. This is important part. Okay, let's see application. Application, one of the amazing application for our job, that is robotic perception, is actually fusion. When you are dealing with many sensors, like the beauty of factor graph shine. So imagine we have cameras, IMU, LiDAR, GPS, like GNS is also kind of GPS, global navigation satellite system. And whatever sensor you have, each of these sensors are giving you like some piece of information, like a piece of puzzle. But each piece can be noisy and incomplete by its own. But if you fuse them together, or if you find a way to fuse them together, this gonna be amazing. And this can be done using factor graph. This is exactly the power of factor graph in this case. The factor graph let you to take all of these different sensor readings and fuse them together into one consistent framework. That's why I'm saying so amazing. It's really useful. And without learning that, we can't deal with the complex environment, the future complex environment. We need to know factor graph. We need to use factor graph. I hope you guys use it in the future. I use that a lot. Right now, I just use factor graph for most of my papers. I publish more than 8 papers just with my name in first name. Other people also with my name use that as well. So, and I love to share this with you guys to maybe you get the advantage of that using your works as well. And how we can deal with these sensors? Each sensor data become one factor. Each sensor act as a factor in a graph, and a graph help you to figure it out as like the best estimate. Because what is the point? The point is finding a state. Like in this robot, I took this picture from Michigan Tech. I think this robot is a famous Michigan Tech robot. Anyway, so the point is to find the state of this robot, for example, using all of these sensors. So this is a state, X, and this is all factors coming from different sources. Factors coming from LiDAR, coming from IMU, coming from radar, coming from GPS, and some of them are between these two, like for example, probably IMU can help to move from x0 to x1, for example, for a dynamic. And this is also have lots of other factors. They are all factors. So empty circles are actually states, and field shapes are factors. As you can see, we can model all of this complex fusion in a solid way, consistent way, using factor graph. And factor graph easily can change to a maximum a posterior and solve in a very efficient way, because it's a sparse. Why is it sparse? Because this x that is unknown and this x are not meshed together. So x0 is just related to very limited points. So when it's very limited points, it means Jacobian matrix that we can see later has most of the parts are 0, and just some of them are valued. They are all 0. When you are 0, you can solve them very efficient, very fast, like in a linear way. So this called a sparsity. A sparsity is very important in factor graph optimization. Okay, so let's clean this up. Anyway, in robotics is very important. You can actually model inference using factor graph. I mentioned inference means what? Inference means MAP, maximum a posterior. Inference means finding X based off this information that coming from sensors. SLAM is using that, simultaneous localization and mapping. We're going to see that soon. Sensor fusion, state estimation, they are all actually can be modeled using factor graph. That's why factor graph can model, can actually model a Kalman filter, can model a SLAM, can model sensor fusion, can model a state estimation, and so many other applications. You just can name it. Like right now, I'm working in some project for a smart grid. A smart grid can be modeled with factor graph. There is another project that I'm working in, a trust management, managing trust between multiple robots, how robots can trust each other when they share information. That can be modeled using factor graph as well. And so many other applications. Anything related to make decision between agents or multiple agents, factor graph can come in. Because making decision means solving maximum a posterior. And maximum a posterior problem is very aligned with factor graph. Why? Because it becomes factors. Maximum a posteriors become factors at the end. Because what is factors? Factors are some little information regarding a state. Like this little information coming from camera, this little information can come from LiDAR, can come from IMU, can come from actually some prior information. Still prior are factors because it gives information about that state. So if you think it's like overwhelmed with lots of things, that's okay. It's gonna get clear soon. You know, when we do in practice multiple projects and a multiple example, we can see that how it works. Okay, let's clean this up. So we can model inference, we can perform and we can perform inference very efficient using some algorithms that exist for nonlinear optimization. We can do actually even new algorithms. We can add new sensors, like some new things coming up. Easily we can fit it in a structure of a factor graph. And in short, factor graph unify heterogeneous sensor data, like sensors that coming from different things, different space, like LiDAR and image, for example, are in different space, and we need to kind of combine them together. And that can happen using factor graph much easier than the other way that we are doing. And this gives us robust perception. Anytime we are talking about robust perception means fusion. Because the only way that we can have a robust perception is doing fusion. Okay. Compared to Bayesian methods, let's compare that with Bayesian networks. Because we talked about Bayesian network last class, factor graph is actually represent constraints. It represents constraints and is very scale efficient. We're going to talk about that more. Scale efficient because of a sparsity that is happen. It supports nonlinear least square. It supports non-square least square. I already explained. MAP optimization. It's going to break down to some of actually squares. And handle loop. That's a very important part. You can have loop in factor graph. What that means? It means you're not gonna have problem of, you know, drifting. Do you remember we had drifting when we are just dealing with just information that we get from sensor and act based of that? We need to, when we make loop, when we are seeing something that we already seen, we can fix all the drift, and that can handle with factor graph easily, but not Bayes. BayeNet is not cyclic graph. It's a cyclic graph. You can have cycle. And enable multi-sensor fusion that I explained. So that was some introduction about factor graph. Next class, we're gonna talk more about that. Any questions about today's class?